The Hall effect has some interest in history behind it. It was one of many experiments that established what form charge carriers had with respect to currents. So let me explain how this works and what the experiment is. So what we do is we have what we have here is we have a piece of conducted material here. It's actually a volume, so to speak, and slab of conductive material, and we have a magnetic field um, that is placed that's perpendicular to the surface here, and we have a current that comes through, and so the current's flowing, as you can see in the picture here, from left to right, and what that's going to do, and you can do your right-handed rule stuff here, but it's going to cause the charges to deflect to the bottom of the conductor here, and you can see we have positive charge building up. And what that does is it starts to establish a positive charge on the bottom there. Well, this is a conductor, so you're going to have some negative charge build up on the top portion. And what that does is it establishes what effectively is, line charges, top and bottom. I mean, really, if this has a thickness to it, which it does, it actually establishes what are effectively capacitor plates here. And there's a voltage that gets established that produces an electric field that points upward. So initially, there's a deflection of charge that builds up in the bottom until enough charge can build up to provide an electric field that points in a direction that establishes a opposite force, and the charge builds up until the voltage reaches a point where the magnetic and the electric fields are equal to each other. And then the charges continue to flow through the conductive material. And the only difference at the end of it all is that the material itself has this potential going from top to bottom. So in this particular example here, if we are looking at positive charge carriers, the deflection is downward, the electric field gets established that's upward, and this is the picture that we have here. Now, on the other hand, if our charge carriers are negative, as is the case with conductors, we would speak of the electron current going in the opposite direction, to the left now. And if we have the same magnetic field, then you're going to have a deflection of charges that are downward, but they're negative charges. So that establishes an electric field that points down instead, and that means the electric force is going to be upward. And you establish also a potential difference across the conductor there, but opposite polarity. The positives are on top and the negatives are on the bottom. And when you conduct this experiment, as you might guess, what happens here is the negative charge carrier scenario is what is observed. The negative charges rest on the bottom, positives are on top. So there's a potential drop as you go from top to bottom here. We call that, again, Hall voltage. Well, we can actually determine what the relationship between these fields are here. So the magnetic force that these electrons experience is given by E VdB, where V here is the drift speed of the electrons. E is the fundamental charge, and B is the magnetic field. This is normally a cross product, but the magnetic field and the drift velocity are perpendicular to each other. Now, when the Hall voltage is established and there's no more deflection, that's equal to the electric force, which is given by E, lowercase e, fundamental charge times electric field. We can express that electric field the way you would for a standard capacitor. The potential difference given by W. W is sort of the width of that conducting piece of material there. We have previously developed an expression for drift velocity that incorporates current, and that's given down here. Now the W times T, that's going to represent the area of the conducting material, and so that's your area. N here is your electron density in that particular material, and so if we substitute that into the equation up top here and we solve for the voltage, we get this nice expression down here. Given a current, and given, now for T, we go back here to show you what T is again. T is the sort of thickness down here of that, which would represent kind of a, it's part of the capacitor, like a part of the capacitor plate area. It's the thickness there. But, the stuff in the bottom here is, just material dependent things, the density, how the conductor's made, and then you establish a magnetic field for a given current, and this is the voltage that you get from that. And it's just a neat little experiment that can be done where you match up the two things and you develop this expression for Hall voltage. So that's all I have to say about it. But again, like I said, it played an important role historically in physics as one of the many things that established that electrons are the charge carriers here. All right. Now, we've talked a lot about force in the last lecture, and forces are exerted on charges that are that are moving in the presence of an external field. Well, the same thing should be able to be applied to currents because that is, again, motion of charge. So in this particular example here, we have a current that flows upward, and we have a magnetic field that points into the page. Now remember that current represents what we would call the flow of positive charge. Excuse me. So we put our fingers upward, and we would take your palm and have it face the screen here, and we extend out our thumb, and we can see our force is directed to the left there. Now, you could do this for electrons as well, of course. You would point your fingers down. You would open up your palm, and your finger would point to the right, but you flip it for an electron. So either way, we see that the force that's established here is pushed to the left. Now, this is horribly exaggerated, obviously. You're not going to see wires bend to this extent unless your magnetic field is, something generated by, like, I don't know, a black hole or something. Like, they're not going to have a field this strong. But, the deflections that are experienced, they're pretty small. Magnetic fields are not incredibly strong. And if you just think about unit-wise here, we're talking about forces that are, a lot of times, for standard magnetic fields and currents, these forces can be measured in millinewtons. In fact, we have a current balance device at campus that we sometimes use for labs. I don't really use it for labs just because the precision that you need to have to see a proper deflection in a wire requires very careful procedures and handling of the equipment, and most students can't manage that, I'll be honest. So I don't really do it because it's just like, it's kind of weird with labs is that some labs can be really simple and easy, and then when we get into a lab that requires a lot more care and effort, students don't seem to be able to want to put in that extra amount of effort. They just expect everything to be sort of the same difficulty. So that makes that one really hard to do. In addition to the fact that it's just really hard to see a deflection anyway. We just take two currents and two wires of current, and we put them on top of each other, and they kind of float. And then obviously the one on top, the one on the bottom stationary, and the one on top wants to fall due to gravity. But if you establish a current in the wires, you can actually have that one levitate a little bit. But again, it's really small interaction. Anyway, so we have an expression for how the force on charges work. It's QV cross B. Now, if you happen to remember, back when we talked about the Biot-Savart law, we did a little trick where we were able to change the Biot-Savart law so that it didn't apply to charges anymore, but it applied to current. And the way you go about doing that is you can rewrite your QV as Q dx dt. You shuffle the dt with the q, and then you have dq dt, and that's your current. And then your dx just turns into some length. So the differential actually gets incorporated into the charges flowing through a small segment of the wire. But we are making the substitution here that QV, when you shuffle around that time derivative, can be written as current times the length of the wire. And so we have this expression here now for the force. You need to know what the current is, and you need to know what the length of wire that you're considering. The length of the wire, this is the length of the wire that's present in the external field. So like in the example that you see here, let me annotate this so you can see what's going on here. The wire has a length that's pretty long. I will draw it out in black here. That's the length of the wire as we see it, but the length of the wire that you would consider for the purposes of making this calculation would actually just be this segment here in red, because that's the only portion that's in the magnetic field. So I is a little awkward in that sense, that you really need to sort of be mindful of what the segment is. And it's weird that it's a vector. Again, we don't really like to, normally we would attach the vector to something like current here, but we really don't want to put direction on the current. So we have a L vector here, which is basically, the magnitude is the distance of the wire, and the direction is just the direction that the current flows. That's what that means there. So L cross B, again, it's a cross product. It involves a sine function. The force will be perpendicular to both L and B and all that stuff that you know from before. Fantastic. Question. Well, actually, I don't have a question. Do I have a question for you? Here, I guess I have a question for you. There is no force. The cross product is 0. The L vector and the B vector are parallel, so nothing. All right. So the horizontal wire can be levitated, held up against the force of gravity. That's the implication here. If the current in the wire is what? Now this wire here will fall if able to, but if you supply a current through the wire with the external magnetic field that's indicated here, what's going to happen? You have option A, B, C. Let's talk it out. Before, we're going to keep you in suspense right now. The force needs to be upward, right? So L cross B. Let's try going to the right first. Right. Open that palm up into the screen. Force is upward. That seems to work. Left to right apparently works. If you go right to left, you're just going to make this thing fall a lot faster. So it is left to right. Excellent. Let's put some numbers.
Professor, could you explain again how you got left to right one more time, please?
Yeah. So I just decided to, there's only two directions for the current, right? Left or right. I just went with right. I don't know why, I just did. So I put my fingers to the right, and again, don't look at me. Don't look at me, you listen to me. Put your fingers, point them to the right of you. Your palm should be opened up towards the computer screen. So I have a computer screen in front of me. And you extend your thumb upward. The force needs to be up to balance against gravity. So the current points to the right. That what we mean by going left to right. The current points right. Well, magnetic field strength and direction will levitate. The 2-gram wire figure. Okay, so now to be clear here, because it's not a lot of explanation, just a picture here. We have current moving to the left here, okay, and the region where the magnetic field's going to be is in a space of 10 centimeters. The section, well, the wire here represents the entire length of the wire, because remember, if we're talking about gravity here, the force that gravity is going to exert is the weight, right, of the wire. And it doesn't matter if the weight, there could be wire outside of the 10 centimeters. That's part of the weight. So anyway, the point here is that the magnetic force is equal to the gravitational force. So that's going to be ILB equals mg. We solve for B here. We get a cozy little 0.13 Tesla. Now that's a pretty big field. If you remember in our discussions about magnetic fields, 0.13 Tesla is nothing to scoff at. That's a strong magnet. That's, again, think about the magnets you put on your fridge. Those are generally in units of millitesla, so this has got to be a very strong magnet. And this wire is puny, 2 grams. You don't realize how much 2 grams is? It's nothing. And it's not much of a current here either. Anyway, what's the direction got to be? Well, we already know that the current goes to the left. Okay, so I'm going to put my right hand, okay, with right hand is going to go to the right, and I have to have a force that's upward. So I'm going to have to put my hand like this, and my palm faces me. That's out of the page. So I'll need to have a magnetic field in the 10 centimeter region that is out of the page of strength 0.13 Tesla. And then we can levitate this thing. 2G. 2 grams. Of course, you got to do SI stuff here, right? So you got to put in kilograms for the calculation. 0.13 Tesla. You can see how hard this is to do as an experiment. I mean, 1.3 amps is not incredibly large, but to have a wire, I mean, I don't want to get all mathy on you, but you could work out what's the diameter of wire. I don't want to get into it, but it's not much. Not much. So we could talk about the force exerted on a wire, and that force that's exerted is established by some external magnetic field. Now, one thing that students get confused about is this: the difference between external fields and internal fields, right? I mean, that got to realize that. Let's go back to this picture here, actually. Right here. So there's a current that goes upward, and we have an external magnetic field that provides a force that's to the left. Now, there's an external field here from something. We don't care what it is, it's just there. However, one thing to realize is that current establishes a magnetic field itself. There are 2 magnetic fields here. What we would call the external field, where the force is where the force comes from, and then there's an internal field, meaning it's caused by the object we're looking at here. So that can be confusing for students, especially if they're already kind of lost with stuff here. But be very mindful of what field we're talking about here. You can calculate a magnetic field due to this current here, but obviously it doesn't interact with itself. It can't do that. So if there's another field that's here due to this current, well, that's outside of this problem. Until we make it part of the problem, let's make it part of the problem. There we go. So what we have here is we have 2 currents. We're going to say they both go to the right. And as a result of that, the currents individually will create a magnetic field in the presence of the other current, which then can supply a force. And in the case here, this will actually cause these wires to be attracted to each other, okay, when the currents run together. So in this case, they're running to the right. So let's look at how this works here. So we're going to look at what the force is on the top wire here. So the force on the top wire is going to be given by its current times the length of wire times the magnetic field produced by the wire on the bottom. So the wire on the bottom points to the right. So I'm going to use my thumb to point along the current, and then I'm going to curl around, and as you can see, if we go atop of that current up here, that magnetic field goes out of the page. So we've established what that magnetic field is. In the presence of wire 1, we have a magnetic field that's out of the page. The magnitude of that field is given by the expression that's right here. Let me box this in so you can see this. But this represents B2. Mu naught I2 over 2 pi d, where d is the distance between the wires. And so if we rearrange things, we have this somewhat confusing looking expression that contains two currents, a distance on top, a distance on the bottom. It's got a lot going on with it, right? And of course, if the field is out of the page, then our right-handed rule for direction of force is going to be current is to the right. I'm going to open my hand out of the screen, and my thumb points down, okay? Now, we can look at what's happening with the bottom one here. For the bottom one, the current on the top produces a magnetic field that points into the page because we're underneath now, so I'm going to curl underneath. It goes into the page. So currents to the right. Open up your palm toward the screen. Thumb is up, and you can see that there's an attractive force between these two wires here. Now, the magnitude that I worked out for the top one is got to be the same as the bottom one. It's got to be the same. Equal and opposite forces. This is basically a Newton's third law argument. But if you want to see how that works, you would put in here an I2 and a B1. But that's just going to give you the same expression here. So, now, let's look at the example of if they go in opposite directions. So wire 1 is going to remain the same, and that means we're going to have an into the page magnetic field in the bottom, but now current 2 goes to the left. And that changes a couple things. The magnetic field on the top now is no longer out of the page, it's now into the page. So we have into the page magnetic fields on the top and the bottom. And this picture is a little deceptive, okay? Because you look at this picture and it gives the appearance that we have an external magnetic field here. And we really don't. We don't. In fact, what's unfortunate here is this should not even be here, to be honest. How do I get rid of that? I just do that. There we go. Well, no, that's worse. No, that makes that. No, that doesn't. Oh, this. Oh, look at this. Watch this. Watch this. Bam. And then I'm going to actually do that in white instead. Oh my gosh, I'm so smart. Look at that. Okay, that's the better picture. Because now it looks like, okay, there's a field up, there's a field down here. I don't know why there was a thing in the middle there. I got to get rid of that after this class is over. All right, so same deal. Same deal here. You have to establish what the fields are in the presence of the wires, and then you work out your right-handed rules. I encourage you to go through with this particular example and prove to yourself that these are opposite forces. So it's kind of easy to think about what's going on here Okay, same currents. Okay, currents go in the same direction. Attractive, opposite directions, repulsive. Which can be a little confusing because you're used to sort of like charges attract, opposite charges repel. Well, don't think about it in that manner because that's not what's going on here. If you say like currents, they attract actually. So don't do the like and opposite for this stuff here. All right. Any questions about this?
Could you go over how you got the directions of the magnetic fields again?
You bet. Let's just do it for this one here. Let me put in my, let me block this out one more time. Okay. So, let's start with the one on the top. Now, the way I taught you originally to do right-handed rules when it comes to current is, I like this one. I mean, you use your thumb to represent the direction of the current, and the way that your right hand curls gives you the direction of the field. It's either going to be, right, it's going to be, it's going to loop one way or it's going to loop the other way. So for the top one, you point your thumb to the right, and then you curl your fingers. Now what you're looking for is, if you're above, it's into the page. Oh no, it's out of the page, right? Out of the page, and then when you're below, it's into the page. So you can also kind of view it. It's kind of hard to do it like this, but underneath, yeah. What's wrong with me right now? Okay, into the page, underneath, out of the page on top. For some reason, my brain broke for a second there. Sorry. For the one on the bottom here, going to the left, goes to the left. On top, it would go into the page. On the bottom, would go out of the page. So again, you just imagine your thumb is the wire here, and you just curl around like this. That's the direction of the field. So, okay.
But like I figured that on the top it'd be into it, and then the bottom it'd be out of it. So why is it both going into the page?
Yeah. So for this one here, let me draw some drew circles. Right. I'm gonna draw the circles and imagine that these are circles that represent the magnetic field that goes around. Okay, so this goes like this. It goes, let me draw the arrows here. Helpful or not, but this would go in, out, in, out. This goes up, down. So if you can imagine that loop in nature, that's where it all looks here like that. So as you can see, when you are underneath, which this wire is underneath, it goes into the page. Now if I do similar circles down here to represent how that field's going to look, it's going to be the opposite direction. So being the opposite direction, it's going to go, okay, in on the top, so like this, down, out, up, in, down, out, up, like this. So that's why on the bottom here, it's also into the page. All right, not yet. That was my problem. I guess I don't have a problem for a little while here. All right, so we can apply this to current loops as well. Loops. So in the picture on the upper left here, okay, if we have our loops identical, it's like the currents are going in the same direction. That's an attraction. And on the bottom, we are going to flip one of those loops, and that's like the currents are going in opposite directions, and it produces a repulsion. Okay? Now, this makes sense when you consider that we've equated current loops to bar magnets. So the one on the left up here, okay, they are redrawn on the right here, identifying how these are like bar magnets. So the magnetic dipole for the left one on the top here points to the right, and the other one points to the left. North and south poles are aligned. That's going to result in an attraction. So again, the way the right-handed rule works for these is you can loop your right hand in the direction of current, and your thumb will tell you the direction of the dipole. So north is to the right for this one up here, and then to the left for the one that's over here, and then we do the same thing for the ones in the bottom there. So for loops, it's a little bit easier to visualize because bar magnets are definitely part of most people's experiences. They kind of get a sense of how those are like, and they know that, you know, the sense of like opposite and like things attract here is a good thing to do because it does apply here. So, all right. I swear I had an example here. I don't know where it is. Give me a minute here. I don't know where my example. Did I skip it? I guess it's near the end. Maybe it's near the end, but it's out of order here. I don't know what's going on. All right, so for a current loop in an external field, not only can you have, you know, translational motion, as you just saw here, you can have things attract or repel, but if any of these current loops are placed at an angle with respect to the magnetic fields, you will also have torque exerted on the loops. And so this picture, a lot going on in this picture here, so just see what's going on here. We got a current loop here that appears that it's counterclockwise. If we're viewing at it from, you know, the perspective we're viewing it from, looks like it's counterclockwise. The external field, it goes through the loop and it points along this z-axis here. The loop is tilted with respect to the xy plane. So what you can do here is you can do for each segment of the wire, you can work out what the force is going to be. Okay, so if you worry about, let's see, the portion on the right here, current is going up. The magnetic field points along the z-axis, so it's going to point over to the right, and you can see that your thumb extends along the x-axis. The opposite's true for the one on the left-hand side. So that doesn't have much of an effect. In fact, if anything, it kind of tries to stretch out the current loop. On the top and the bottom, you have a similar thing happening there. The forces are up on the top and down on the bottom. Same deal. It's kind of pulling on those things. But because there's an angle here, these forces have a distance between them. Okay, and what you see down here are the moment arms. Moment arms being the distance from the horizontal distance from where the force is applied to where the radius is, right here. So as you can see down here, we use L to represent the length of one of the sides of the wire here, and so we can relate this with a sine function. This dotted line here would represent half of L, and we want the side opposite, so that's going to be D. So we can see here that D is 1/2 L sine theta. And that's just the moment arm. You double this to get the full distance between them, which we're going to eventually need. So the forces of magnitude, ILB. The moment arm is 1/2 L sine theta. We're going to double that in a minute here. So we double that because we want the full distance between those forces. And so we can figure out what the torque is. The torque, right? The definition of torque is, R cross F. Or if you have moment arm information, then it's just FD. We have two of them. That's where that factor 2 comes in. Our force is I B sine theta. As you can see here, if we put in our expression for D, the 2's cancel out. We get another factor of L here. And we get our sine theta. Now, the L squared is the area of the loop. And so that thing in the front here, we've already defined what that is. That's the dipole moment vector magnitude. So I times an area, in this case here, L squared is the area. So this whole expression becomes mu b sine theta, which has the form of a cross product, and it is a cross product. So the torque vector is given by the dipole moment vector, mu, cross B. And what this tells you is not only the magnitude of the torque, but it tells you the direction that this thing is going to rotate. So I know you're probably completely sick of right-handed rules by now. Okay? But you would point your fingers along mu, okay, which for me would be like up and to the right here. And I open up my palm along the z-axis, and the way that you rotate your hand represents how it's going to rotate. The torque vector's direction is along the positive x-axis here. So we can see that this thing's going to rotate. If you're looking along that x-axis there, it's going to rotate clockwise. And what would happen here is if there's no dissipative forces, it will just kind of oscillate back and forth. If there is dissipative forces, then it's going to dampen down and then just come to a halt there. And as you can imagine, we have a very similar situation that we dealt with back when we did electric dipoles, where there's a balanced, like a stable equilibrium and an unstable equilibrium. Here we are close to the stable equilibrium. If this were to flip 180, that's the unstable one, meaning if you were to nudge it, you would cause it to flip over very rapidly. It would experience a large torque. Okay, but if it's already sort of upright and you nudge it, it's just going to return back to equilibrium. So we have the same situation here. There's a lot of analogies back to the electric dipole stuff here. Lots of stuff. All right, so this question here, if released from rest, the current loop will do what? What's the current loop going to do here? There's a lot going on, sort of, in this. You're going to want to first figure out the direction for mu, and then from there figure out your torque. So, oops, I clicked it accidentally. It's definitely confusing. I'll give you that. Definitely confusing. All right, let's talk about it. First thing to establish is the direction of mu. You take your right hand, you curl it along the current here. So on the left-hand side, we go into the page. On the right, we come out. So if you do that, your thumb is pointing downward. Downward. So mu is down. So let's draw that. I'm going to draw mu being down. I'm going to draw it big just to make it look different. Because what you're seeing here, these are the forces that are being exerted on it. You can do that, but we just define mu cross B. So this is mu. Let's do mu cross B. Your fingers need to be downward. Your palm should open to the right because the magnetic field's to the right. And we're going to curl our hands like this. When I curl my hands like this, that's counterclockwise. The torque vector points out of the page, but that results in a counterclockwise rotation here. Now, you could just visualize it with the forces, which I don't really want you to do because I just didn't go through all that explanation for nothing there. But if the current's into the page here, the force is down on the left. And if the current comes out of the page on the right, the force goes up. So you can see from the forces, that's going to cause a counterclockwise rotation here. We want to know what the net force on each wire is. We got 3 wires. Okay. We got a 10 amp going to the right. The middle one's a 10 amp going to the left. We got another 10 amp on the bottom here. Okay. Yes, I have themed it Christmas-y. I set up my Christmas tree. Somebody asked me what I did this weekend. We set up our Christmas tree this weekend. Yep. I wanted it up earlier, but my family thinks I'm nuts. Okay. So, all right, before I get into this, let me tell you something here. If you're already confused about stuff, this is not going to help you. You're going to feel a lot worse right now. However, that should be an opportunity, right? You view that as an opportunity, a challenge. one thing that's sort of nice about some of these problems is there's like one problem that kind of just explains it all. And this is a kind of example that when we're dealing with forces on wires, doing a problem like this and really going over it repeatedly and really understanding what's going on here, while very challenging, is very rewarding too, because if you get this example, then you really get what's going on here. So if if this is leaving you confused or you're a little uncertain about this, spend some time, go over this again. Okay, let's look. Now, I want the force on each wire. So I'm going to do first the wire on the top. If I'm going to do the wire on the top, I have to know what kind of magnetic fields are present to produce a force. There are two wires below it. Those two wires are going to produce two different magnetic fields that will exert a force on the wire. So I've color-coded the second wire red, and the third wire I've color-coded to be green. So when I draw the fields up here, you can see the colors correspond to the wires they come from. Now the current from wire 2 goes to the left, and so put your thumb to the right, to the left, and then above the wire we're going into the page. So you see a bunch of red X's up top here. Fantastic. On the bottom here, the current goes to the right, so when you're above the wire, it's coming out of the page, the magnetic field. So I have green dots up here. So that's what the fields are like up here. The only thing that's not properly illustrated in the picture is that the green the green magnetic fields are weaker because it's farther away. Great. So the force exerted on that wire is going to be given by IL times the magnetic field. That would be the net field. There'd be two fields there. I've drawn vectors here that illustrate what those relative forces are. The green one is a weaker field, so there's a weaker force there. If current runs to the right and the field is out of the page, then the force is down. For the red, the current goes to the right, the field is into the page, so the force is up. So if you draw F of 2 on 1, it should be a little bigger than F of 3 on 1. Now, let's go down here to the calculation. My current's 10. That's the current in the wire of interest. The length that I'm considering is 50 centimeters, so 0.3. And then I have two different expressions here. The magnetic field due to wire 2 and the magnetic field due to wire 3. I have a negative here because I've identified in my initial setup that this force is downward. I'm calling down negative. And you put in all your numbers here and we get a 2.5 times 10 to the minus 4 newtons. Okay. Now, wire 2 is 0. Why? Because the magnetic field in the presence of 2 is 0. Okay, there's a magnetic field from the top and a magnetic field from the bottom, but they go opposite directions and they're the same distance from the wire, so it cancels out. Okay, so the top wire, okay, current to the right, curl underneath, okay, into the page, magnetic field. The one on the bottom is an out of the page magnetic field, so that's 0. F3 is equal to F1, but negative. It's completely identical to wire 1, except everything is flipped around. Okay, we're below this time instead of being above. And everything is flipped around, so we have the exact same treatment. Everything's the same here, except when you get down to put your forces in, okay, the arrow that, see this big arrow that points up here, and the small arrow that points down, that's flipped down here. So the big arrow points down, the small arrow points up, everything else is identical. You just put a negative in there. Now, I mean, either you can see that symmetry and make that assertion, or you can just go through and do the exact same treatment for 1 and work all those numbers out, but you'll get the same thing. And I encourage you to do that. That would be a good exercise to do. Okay? So, that all being said, do you have any questions about this? Is anything unclear about the explanation for this?
Could you explain why the force on 2 equals 0?
Yeah. So you were looking at the magnetic field around 2. The current on the top, because it goes to the right, is going to have a magnetic field below it that goes into the page. The one underneath it is going to have a magnetic field above it that comes out of the page. Okay, now just remember, these two currents, the top and the bottom, have identical magnetic fields. Okay, they go under and over, under and over. They go under and go into the page, and they go over and out of the page. So because of that, one of them is going to have, and the top one has an into the page, and the bottom one has an out of the page. Those cancel out. Not just because they go opposite directions, but also because they're the same distance from wire 2. So both those factors matter here. Okay. I mean, if you were to write it out like I did for number 1 here, you would have the exact same thing that you see down here, except there'd be a 0.02 here, and that means these two magnetic fields cancel out. All right, now you're not done with this, right? Of course, I'm going to give you homework. It's going to involve a lot of this stuff here, but this is a lecture that I think everybody needs to spend more time on and think about. This is not easy stuff. It's a lot going on, a lot. So my advice to you is to learn it. Oh, well, that's good. Good to hear. Okay. Let's keep going. I got some other things to talk about. So, you may ask yourself this question. Why are current loops and bar magnets similar in terms of their magnetic fields? Well, let's think about what it means to be a bar magnet. You have a bar magnet has a built-in field. Right? You take 2 bar magnets, put it near each other, you got an interaction. And so one thing that may be confusing to you at this point is sometimes charges move and there's magnetic fields, and sometimes it just exists in a piece of metal. What gives? Well, the answer to that is it's all about move and charge. And when we're thinking about magnetic materials, you got to start looking at things at the microscopic level. Okay? An atom, in a very traditional depiction, like the Bohr model of the atom, the old school way of doing it, you have a positively charged nucleus, and you have an electron that's flipping around. That's motion, that's movement. And so that electron that's flying around, guess what? That's current. Those electrons that are flinging around that atom, again, from the very traditional standpoint that we talk about these things, is a current. So in the example that you see here, the electron is going in a clockwise direction, so the current would be counterclockwise here, and that would produce a magnetic dipole that points upward here. And you loop your hand around with the current, and your thumb points upward here. So that is a little tiny magnetic dipole, and it would have a magnetic interaction. It has a north on the top and a south on the bottom. So that's what that looks like. It's because of that electron spin. Sun smells really bad. Ugh. All right, now, if you have a piece of material that is not magnetic, what's happening there is every atom has a natural dipole moment to it, a magnetic dipole moment. But in materials that are not magnetic, these dipoles are sort of frozen in a particular random direction. And these things are not free to move. And so what happens here is the net magnetic field in the substance is basically zero. If everything is randomly distributed here, and so that's why some material just doesn't do anything with from a magnetic standpoint. Because everything's just stuck in random orientations here. Now there are materials that by themselves don't produce magnetic attraction, but when brought in the presence of an actual magnet can have an attraction there. And what's occurring there is the fact that when brought in the presence of a magnetic field, the molecules or the atoms or whatever do have the ability to move, to at least shift their orientation, and they can have their magnetic fields line up. And as a result of that, they can experience magnetic phenomenon. Okay, it all really comes down to the material properties. Okay, in this example right here, you have randomly included dipole moments, and they're not going to be able to move. Even in the presence of a magnetic field, just the structure on the microscopic scale does not allow anything to move here. Yeah, well, ferrofluids are a good example of that. In fact, all the stuff we're talking about here is called ferromagnetism. And ferromagnetism is just it's magnetism produced by electron spins. So something like a fluid, of course, has the ability to have their atoms experience translational motion. I'm talking about like a paperclip, for example. Paperclips are not inherently magnetic, but you place a magnet near them and they're attracted. Because what happens is inside the paperclip, while you can't have atoms physically move, like translationally move, they can rotate. So they can have their magnetic dipoles line up. And then it takes on a magnetic behavior. Okay, so if we were to look at how do you make so something like an actual magnet has their dipoles lined up and locked. So imagine we go back to this figure right here. Now they're all randomly configured and they don't have the freedom to move around at all. But what you can do is you can change the magnetic properties of these things if you heat them up. So you heat up the metal, and heating up the metal allows things to start to freely rotate. They line up like this, and then you rapidly cool them so that they become stuck again, but now we've lined them up this way. And so when they get stuck, they stay lined up. And then that becomes a true magnet. You don't need to put it near anything else. You have basically locked in its structure that magnetic behavior here. So now that can happen. It doesn't happen perfectly. We usually have what we call magnetic domains, where there are regions where on a large section of it, you have things that are sort of randomly ordered, but may not completely add up to zero here. Okay, here's what I was talking about for the creation of those fields. So this solenoid here is placed near this metal, and if the material is ferromagnetic, then the dipoles can line up, and so this becomes magnetic. And I don't have that here, do I? And anyway, so a permanent magnet can be created if you heat the stuff up, supercool it as the magnetic field is placed through it, and then those domains become locked. And everything is lined up, and then you've created that magnetic effect.